Welcome to lesson 39, AC generators, RMS and transformers. Today we finish magnetism. Here's the plan for today. Let's take our coil from last lesson, but instead of sliding it in and out, spin it steadily in the field. You're still cutting field lines, but as it rotates, the angle changes, so only the cosine component counts, which means the flux linkage is BAN cos omega t. And Faraday tells us that EMF is the rate of change of that, so we differentiate. Differentiating cosine gives minus sign, and the chain rule pulls out a factor of omega, so the EMF is BAN omega sine omega t. Keep that omega and mind the sign. And look at the result, a sine wave. Spin a coil at constant speed and you get a smoothly alternating voltage out. That is alternating current, and that's what comes out of every power station in the country. It's rather satisfying. Sliding it in sinusoidally or spinning it round gives you exactly the same output. But there's something we need to consider. Back EMF. Run a motor and the coil is spinning in a field, which, by everything we just said, generates an EMF of its own. And by Lenz's law, that EMF is opposing the supply voltage that's driving it. So from V minus epsilon equals IR, when the motor is running smoothly, there's little back EMF, so the current is large. Once it's up to full speed, the back EMF is large and the current drops right down. That's why a motor draws a huge current at the moment you switch it on, and much less once it's spinning. And that's why starting a motor is when things trip. Now a genuine puzzle. An AC voltage is swinging up and down constantly, spending as much time negative as positive. So its average is 0, which means it's completely useless. When we say the mains is 230 volts, what do we actually mean? The answer is the RMS value, and the definition is the useful bit. The RMS current is the DC current that would deliver the same average power. It's an equivalent DC value. And you can see where the root 2 comes from. Power goes as I squared, so the power curve is always positive, and its average turns out to be exactly half the peak. You can picture it as folding the peaks down into the troughs to level it off. So set I RMS squared R equal to a half I naught squared R. The R cancels and you're left with I RMS equals the peak current over root 2. Same for the voltage. The average power is the two RMS values multiplied together. Now the grid has a problem. Electricity is needed in different forms for different uses, and it has to be moved around as efficiently as possible. The transformer solves this, and it's beautifully simple. Two coils wound on a shared iron core, but not connected to each other at all. No wire runs between them. The alternating current in the first coil creates a changing magnetic field in the core. That changing field passes through the second coil, and by Faraday's law it induces an EMF there. They torque purely through magnetism. And the ratio of the voltages equals the ratio of the number of turns. Vs over Vp equals Ns over Np. More turns on the secondary and you step up the voltage, fewer and you step it down. Transformers are remarkably close to 100% efficient, and there are 3 design reasons you should know. The windings are made of low resistance wire to minimise heating losses. The core is laminated, built in thin insulated layers, which stops eddy currents from circulating around it and wasting energy. And the core is made of soft iron, which magnetizes and demagnetizes easily, so it can keep up with a rapidly alternating current. And here's why it all matters. The power lines that crisscross the country run at enormous voltages, hundreds of thousands of volts. Why? Because power is I times V, so you can deliver the same power either with a big current and a small voltage, or a small current and a big voltage. And the energy wasted heating the cables is I squared R. It depends on the current squared. So half the current and you quarter the losses. So we step the voltage way up for transmission, which drops the current right down, which slashes the losses. Then we step it back down again near homes and factories which need it at safe, usable levels. Step up to travel, step down to use. And 2 numbers to have at your fingertips. UK mains are 50 Hz at 230 volts. Make sure you learn these. That's the end of the video and the end of the topic on magnetism. Thanks for watching and check out my tutoring page below.